Welcome to this explainer. Look, what if I told you that the exam you're preparing for doesn't actually exist in the way you think it does? When most students sit down in that exam hall, they look at a Cambridge Physics past paper and they see a series of random, terrifying questions. But when examiners look at it, they see something completely different. They see code. They see a matrix of very specific assessment objectives, trigger words, and hidden patterns. There is no paper. There are only patterns. And today, we are going to learn how to see the code behind every single question. We are diving deep into the Cambridge IGCSE Physics, specifically code 0625, focusing on density. But we are not just going to recite textbook formulas. No way. We are going to decode the reality of the exam strategy. We are going to explore the hidden examiner expectations that are buried inside those principal examiner reports, and we'll use density, one of the most foundational topics in the entire syllabus, as our key to unlocking the matrix.
Okay, let's dive right into this by acknowledging the absolute stakes here. Density, along with all its related concepts like pressure and buoyancy, can account for a massive 15% of your total examination marks. 15%! That is the literal difference between two entire grade boundaries. To truly understand how to capture those marks, let's picture two typical students facing a standard, high-stakes 6-mark question. You know the one. Describe an experiment to determine the density of an irregularly shaped rock. Let's call our first student Alex. Now, Alex is smart, Alex is studied, but under pressure, Alex overloads. Panicking, Alex just dumps raw, unfiltered physics facts onto the page. Alex writes that density is mass divided by volume, that solids have tightly packed particles, that mass is measured in kilograms. It's all completely true. But guess what? There is absolutely zero analysis. Alex hasn't answered the specific command word. Then we have our second student, Sam. Sam is the opposite. Sam rushes. Sam is racing against the clock and scribbles down, "Put the rock in water" to see how much the water goes up, then weigh it and divide the numbers. Sam completely misses the required precision in terminology. Both Alex and Sam are practically taking that critical 15% and throwing it out the window. Today, we are going to completely fix that.
To secure these marks and completely change how you approach this paper, our explainer today is broken down into this precise 4-part playbook: core principles, the procedural framework, top examiner warnings, and mastering evaluative thinking.
Let's move right into Section 1, the core principles of density.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so what's really fascinating about this foundational concept is that true mastery isn't just knowing the formula, rho equals m over v. That formula is just your entry ticket. It gets you in the door. True mastery is applying it logically to everything from water displacement to buoyancy. To truly unlock the matrix of the marking scheme, we need to understand the physics-specific assessment objectives. Examiners use very specific command words. Words like state, describe, calculate, and evaluate. Each of these is a unique piece of code. To hit these perfectly, top students use a structured blueprint. We call it the Peel framework: point, evidence, explanation, and link. Think back to our student Alex, who just threw facts at the page. If Alex used the Peel approach for that irregular rock question, the answer would completely transform. First, the point. To find the density of the irregular rock, we first need to determine its mass and its volume. Boom, clear and focused. Next, the evidence. Using a top-hand balance, measure the mass of the dry rock in grams. Then the explanation. Find the volume using the displacement method. Fill a Eureka can with water up to the spout, gently lower the rock in on a thin string, and collect the displaced water in a measuring cylinder. Finally, the link. The volume of the displaced water is exactly equal to the rock's volume, which is then divided into the mass using the density formula. Do you see the difference? It's structured. It's undeniable. It gives the examiner exactly what they are looking for in the exact order they want to see it.
Now here is a secret straight from the examiner reports. Cambridge explicitly notes that candidates who preference cross-topic connections, meaning they can apply evidence-based reasoning to unfamiliar blended contexts, achieve significantly higher marks. You simply cannot keep density in a neat, isolated little box in your brain. The examiners love to combine topics to test your real understanding. For instance, they might ask you to calculate the density of a liquid, and you think, great, easy marks. But then, the very next part of the question suddenly pivots. Now they are asking you about the pressure exerted by that exact same liquid at a specific depth. Suddenly you need to pull in the formula, pressure equals density times gravity times height. Or they might tie density into forces. They might ask you to explain why a massive, heavy steel ship floats while a tiny, solid steel block sinks straight to the bottom. This forces you to connect the concept of density to upthrust, displaced volume, and equilibrium. If you can clearly articulate these causal relationships using your structured Peel framework, you are proving to the examiner that you don't just memorize, you understand. And that is how you capture the top-tier marks.
So, the absolutely crucial point is how we actually execute this under exam conditions, which brings us to Section 2, the procedural framework.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to the matrix. This slide brilliantly illustrates the exact step-by-step procedural framework you must use when tackling any complex density problem from past papers. This is your physics success blueprint. Let's actively apply these 5 steps to transform how our rushing student Sam approaches a question. Step 1. Deconstruct the question. You literally take your pen and circle the command word. Is it calculate? If so, you know you need a formula and numbers. Is it describe? Then you need a chronological method. Step 2. Extract relevant data. Pull out the given mass, the dimensions of the solid, or the initial and final volumes on a measuring cylinder. Write them on the side of the page so your brain doesn't have to hold them. Step 3. Select the analytical framework. Bring in your Peel structure for written answers or your standard formula substitution layout for math. Step 4. Execute with clear notation. This means explicitly writing out your working. Do not just punch numbers into a calculator and pray. Write down the equation. Write down the substitution. Step 5. Present with correct terminology. This is where Sam lost all the marks. We don't write weigh it, we write measure the mass using a balance. We don't write see how much water goes up, we write measure the volume of displaced liquid. This 5-step blueprint completely eliminates the panic of brain dumping and ensures you meticulously hit every single required detail on the mark scheme.
During this execution phase, your practical application absolutely must demonstrate these specific data interpretation skills. Let's do a quick interactive workshop right now. Imagine a complex data table on your screen. It lists initial volume, final volume, and mass of a liquid in a beaker. Challenge 1, data scan. You have limited time in the exam to extract the core trend. Are you just looking at the raw mass, or are you realizing that you need to subtract the mass of the empty measuring cylinder first? That is a classic trap. The examiners are testing your professional scientific skills here. When you read the volume of that displaced water, are you explicitly stating in your answer that you must read from the bottom of the meniscus at eye level to avoid parallax error? Those are the micro details that separate an average grade from an A star. You have to interpret the physical relationships perfectly. Think about this. If the mass of a metal block remains constant, but its volume increases because it's being heated and undergoing thermal expansion, what happens to its overall density? Well, since you are dividing a constant mass by a larger volume, the density decreases. Being able to draw these logical, evidence-based conclusions on the fly, step by step, is exactly what the examiner's code requires.
Let's shift our focus to the pitfalls. Section 3, top examiner warnings. This is what the senior examiners are desperately trying to warn you about. If you look closely at these top 3 mistakes straight from the principal examiner reports, you'll see a clear pattern. They all stem from rushing, not reading the code, and ignoring the strict conventions of the paper. Let's make this highly practical with Challenge 2, find the flaw. I'm going to read you a flawed sample paragraph from a real past paper attempt, and I want you to spot exactly where the student threw their marks away. Ready? I measured the irregular object's volume using a displacement can. Then, I placed the wet object on the balance to find its mass, and finally divided the mass by the volume. Did you catch it? The fatal flaw, the absolute grade killer, is measuring the mass after putting the object in the water. The wet rock is going to have water clinging to it. It will have an artificially higher mass, which completely ruins the density calculation. The correct sequence is always dry mass first, then volume. Examiners note this specific contextual mistake constantly. Another massive issue is providing generic answers. When a question asks you to explain why a specific object floats, you can't just write, because it is light. That means nothing in physics. You must rely on a structured contextual approach. Point out the specific density difference between the object and the fluid. State the actual values if they are giving. Explain that the upward buoyant force, the upthrust, is equal to the weight of the displaced fluid, and link that to the object achieving equilibrium at the surface. Specificity is the ultimate weapon against losing marks.
To permanently avoid those traps, we need to level up. Section 4, Mastering Evaluative Thinking.
This comparison right here is the ultimate cheat code. It shows that to reach the highest possible grades, you must actively question assumptions and identify limitations. Average candidates provide superficial breadth. When they calculate the density of an irregularly shaped solid using the displacement method, they do the math, write down the final number, and just move on. But a top-scoring candidate, someone who sees the matrix, demonstrates evaluative thinking. They question the very assumptions made in the experiment.
Let's do challenge 3, speed writing. If you had 30 seconds to add an evaluative sentence to your paragraph to guarantee top marks, what would it be? You might add a sentence noting, "This calculation assumes that the string used to lower the object has negligible volume, so it doesn't artificially inflate the volume reading." Or perhaps, "This method assumes the irregular solid is not porous and does not absorb any water," which would alter both its mass and the volume of water displaced. By identifying these subtle experimental limitations, you are evaluating the quality of your own evidence. You are showing the examiner that you aren't just a robot reciting a textbook, you are thinking dynamically like a real physicist. You are justifying your analytical decisions. This level of critical depth is precisely what separates the good from the great.
Now let's see how all of this builds into your ultimate exam safety net. I literally cannot emphasize this method marks strategy enough. The process is just as important as the final answer, and hiding your calculations will severely cost you. Think back to our student Sam. Sam is always rushing. Let's say Sam actually extracted the right data. Sam punches the mass and the volume into the calculator, gets a final number, and just scribbles that final number directly onto the answer line. But what if Sam was stressed, misread the measuring cylinder slightly, and typed a 4 instead of a 5? The final answer is completely wrong. And because Sam showed 0 working, the examiner looks at the page and has no choice but to award absolutely 0 marks. Now imagine you follow our procedural framework. You explicitly write down the formula, rho equals m over v. You write out the exact numbers you extracted from the data table. You clearly show the division step. Even if your finger slips on the calculator and you make a simple mathematical error on the very last step, the examiner will look at your clear notation. They will see that your physics logic was flawless, and they will award you the method marks. In Cambridge physics exams, the journey you show on the page is literally worth more than the destination. Method marks are your insurance policy against exam stress.
So, let's quickly recap our complete answering system. First, command word decoding. You absolutely must understand exactly what the examiner is asking before you write a single word. Second, Peel framework application. Use a structured approach to build your paragraphs and completely eliminate that panicked brain dumping. And third, use a step-by-step time management matrix. Extract your data efficiently, show your working, and don't rush the process. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. As we wrap up this explainer, I want you to take a hard look at your own study habits. Are you prioritizing the final answer at the expense of your methodology? In a subject where the process is the proof, are you leaving 15% of your grade to chance just by hiding your work? Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.